Welcome to the Educational Series Part 2 on how to control an inverted pendulum. If you still have not watched Part 1 and Part 0 to understand how to derive a mathematical system model for the inverted pendulum, please go back and watch them. In this video, we are going to go over the linearization of a nonlinear system and what problems can occur. Generally, linearization is performed about a certain point. Let's take a quick look at parabola to understand why we need to linearize about a certain point. Parabola in red represents our nonlinear system. The goal of a linearized system, line in orange, is to approximate the behavior of an actual nonlinear system. As you can see, if we are close to the point of linearization in black, the line is pretty close to parabola. However, the farther we move away from the black point, the estimation becomes less and less accurate. Our goal is to eventually get the pendulum pointing up, so that is the point about which we are going to be linearizing. Therefore, our linearized system will be able to control the inverted pendulum only when the initial position of the pendulum arm is close to an angle upward. Let's take a quick look at how the linearized control for inverted pendulum behaves. We are starting at x position -100, and our goal is to end up at x position 0 with the pendulum pointing up. The first simulation on top is for initial angle of 6 degrees. As you can see, our control system manages to reach the goal. Second simulation is for initial angle of 90 degrees, and it obviously fails to reach the goal. Going back, we have 4 states: our position, velocity, angle, and angular velocity. Our goal is to have x position equal to x, because none of our state equations are dependent on x. Therefore, our system is indifferent if x is 0, 100, or 1,000,000. Velocity is equal to 0 because our acceleration is dependent on velocity. If there will be even small velocity at the end, it will cause an acceleration that will destabilize the whole system. Pendulum angle theta is either 0 degrees for pendulum pointing upward or 180 degrees for pendulum pointing down. This is the condition we want to satisfy. And lastly, similar to velocity, we want our angular velocity to be 0. To linearize our system, we need to use Jacobian matrix that will be multiplied by our states, which are position, velocity, angle, and angular velocity. Below are the state equations that we derived in Part 1 of Educational Series. Each equation is assigned to a row vector c. For example, c at row 1 is equal to velocity. Looking at the Jacobian matrix, we are taking derivatives with respect to our states, x1 position, x2 velocity, x3 angle, and x4 angular velocity. On the bottom right of the matrix, we specify that our states will be assigned the values about which we linearize. As an example, let's take derivatives for C2 with respect to 4 states to fill out the second row of Jacobian matrix. Derivative with respect to position is 0. Derivative with respect to state 2, which is velocity, is equal to -bm L over L times m plus m minus m times cosine theta squared. When we make theta equal to 0 or pi, m minus m times cosine theta squared is equal to 0. This simplifies our equation to -bm over cart mass m. Derivative with respect to state 3, which is angle theta, is equal to -mlg times cosine theta squared minus sine theta squared all over L times m plus m minus m times cosine theta squared. When we make theta equal to 0 or pi, cosine theta squared minus sine theta squared is equal to 1. This simplifies our equation to -gm over m. Derivative with respect to theta dot is equal to bm times cosine theta plus 2 theta dot ml squared times sine theta all over L times m plus m minus m times cosine theta squared. Making theta equal to 0 or pi and theta dot equal to 0, our equation simplifies to plus or minus bm over lm. To take care of plus or minus, we assign a variable alpha, which is equal to +1 when the pendulum is pointing up and -1 when the pendulum is pointing down. These derivatives were done for each element in Jacobian matrix, and we get the following matrix. Additionally, we need to do similar derivatives for the input matrix to understand how our linearized system reacts to our input of force U. For the input Jacobian matrix, we get the following vector, and cleaning it all up, this is what our linearized state space should look like. Next, let's take a look at how to program a control system for linearized inverted pendulum in Matlab. We create a function called stabilize, which takes initial condition of the cart position and velocity plus pendulum angle and angular velocity. Our initial conditions are negative 100 meters for position, 0 velocity, 0.1 radians for angle, and 0 for angular velocity. First of all, we initialize our parameters, such as cart and ball mass, pendulum length, and so on. Then, we need to specify our alpha, which came from Jacobian Matrix, with alpha equal to 1, linearizing the system about upward pendulum, and alpha equal to -1, linearizing the system about pendulum down. Next, we write our linearized Jacobian matrix into A for states and B for input force U. Then, we need to create an optimal controller K that will set force U based on the error between what our goal is, which is pendulum upward, and our current states. LQR stands short for Linear-Quadratic Regulator, which tries to minimize the cost function displayed. This cost function minimizes the required energy to reach a certain goal. To minimize this cost function, one needs to solve Riccati equation displayed. We need to solve it for matrix P, which is the only unknown. Then we would need to apply it to our controller K, which is equal to R inverse times B transpose times P. Even though it is all so much fun, we will just use Matlab to do all of that for us. However, here is a quick example on how one would solve a simpler problem. Please pause the video to go over the example at your pace. So now that we have our controller K, we can control our inverted pendulum. We are going to simulate how we are controlling the inverted pendulum starting at 0 seconds until 150 seconds at time increments of 0.01 seconds. To simulate the inverted pendulum, we are going to apply ODE45 on our function called inverted pendulum. We are passing all our parameters such as mass, length, and so on. In addition, we are specifying the time interval and our initial condition y0. Let's take a quick look at inverted pendulum function. So first, we set our reference or goal, which we are trying to achieve. For us, it is for the cart to end up at position 0 with the pendulum pointing upwards. Then we need to calculate how much force our controller thinks we need to apply to reach our final goal. It takes our current states that are stored in vector y and subtracts the reference values to see what is the difference between them. If we are close to our reference values, this difference will be small and it will result in having smaller force applied. So then we extract states from our y vector. Again, position is y1, velocity is y2, angle is y3, and angular velocity is y4. Then we plug them into our state equations that we derived in part 1 of the educational series. Please note that dy1 is simply derivative of state 1, which is position with respect to time. And we know that derivative of position with respect to time is velocity. Then our second state is velocity. So derivative of velocity with respect to time is acceleration. ODE45 will multiply these derivatives by the time increment and calculate our states for the next time step automatically. Going back as the result of ODE45, we get a time vector and our states y. Here you can see our time vector, which has a length of 15,001. As intended, it starts at 0 and goes until 150 in time increments of 0.01 seconds. Y vector has 4 columns that correspond to position, velocity, angle, and angular velocity. As initialized, we start at -100 meters for position, 0 velocity, 0.1 angle, and 0 angular velocity. Then we have the values at different times that correspond to the time vector. So the length of y vector is equal to the length of time vector, 15,001. So let's draw our pendulum using the position and angle from vector y. We can set new position and angle by clicking on the screen, but sometimes it will freeze because our linearized controller fails so badly that ODE45 cannot even process it. This is it for linearized control. Next, we will see how to create a complete controller that addresses these issues and makes sure that we can stabilize our inverted system out of any position.